Alright, this is a walkthrough video of how we develop the relationship between forces and deformation in two parallel members of different material. They're subjected to a temperature load only. Okay, so again, it's two separate members bonded together so they act as one. Okay, so immediately we have to think of, since we have temperature change, we're going to think of alpha T, the coefficient of thermal expansion, and we're going to say in this problem alpha A is greater than alpha B. Okay. Also notice that LA equals LB, and also finally that delta A equals delta B. All right, this is going to be our compatibility condition. All right. Okay, so this process will help you understand, the behavior of the material and then how to relate it to the next topic where we add a concentrated load to the system. All right, so let's talk about the two materials. Right, so we know that since alpha A is greater than alpha B, okay, that the material A wants to expand quicker than B. So it wants to get longer quicker than B. Okay. All right. So really, as A tries to get longer, so as A tries to get longer, as it tries to lengthen, it pulls up on B. Okay, because it's trying to get a little bit longer, right? So if I think of A getting just a smidgen longer, as it tries to get longer than B, it pulls B up to make it the same length. Okay, and conversely, as B resists A's pulling, equal and opposite, remember, B pulls down on A. Okay, so that's what's happening. So if we kind of think of it, a little bit visually, so to speak. All right, if I have this member, and I separate them, right, there's member A and B. All right, so A is here, B is here. Again, A tries to get a little bit longer, it's pulling up on B. And as B tries to stay shorter, right, as B tries to stay shorter, it's pulling down on A. So we see that A is in compression to resist that downward force, and B is in tension to resist that upward force. Okay, so that's how we end up with these assumptions, that A is in compression and B is in tension. Okay, so this could be the thought of the effect on B from A. This is the effect on A from B. Okay, so they interact with each other and they have an influence on each other. Okay, so now you see that we have P in member B and we have P in A, and we start to see equilibrium developing, right? We see equilibrium developing. So we can sum forces in the y up is positive equal to 0. 0 equals plus PA minus PB. So therefore PB equals PA, right? So there's one equation, but two unknowns. Okay, that's indeterminate. So now we have to develop a second equation using our condition of compatibility, right? And we know what that condition is. Here's the condition. A change in A has to equal change in B. So using compatibility, we know delta A has to equal delta B. Okay. We know LA equals LB. So therefore we could say strain in A equals the strain in B. But let's focus on, again, focus on the change in length, right? Okay. So when we do that, we see that delta is composed of two components. We got a delta due to the temperature change, and we have a delta due to the applied force P. Okay, and so let's write those equations. So delta A, remember it's in compression, has to equal delta B, and remember it's in tension. Okay, the components of A are delta A due to the temperature change plus delta A due to the axial force P equals delta B due to the temperature change plus delta B due to the internal force, the internal axial force. And we know those expressions for change in length due to temperature. It's alpha A delta T LA plus PA LA over area A EA. But remember that P is in compression, so we want to make this negative. All right, it's going to be a negative change in length due to the axial compression. Over here, same thing, alpha B delta T LB plus PB LB over the area of B and the modulus elasticity of B. This is in tension, so this is okay as being positive. Okay, again, remembering that LA equals LB, right? Right, remembering that, we can factor out the L's, factor out LA and LB, and LA equals LB, so all the L's drop out. So it's independent of length. So we can cancel that, cancel all those L's. So what we're left with is this expression. Oops. Okay, so that's the expression that we can use. And notice we have another equations in terms of A and B. Okay, and then we can solve for that and plug into PA equals PB, right? So we could substitute PA equals PB and solve for P, right? You know, we just have to remember that alpha A is greater than alpha B, which results in delta T is greater than 0, and then that means A is in compression and B is in tension. And if you get a negative value for any force P, that means those materials are opposite of what we assumed. And again, these are our assumptions. Okay. And we can then use this expression here to solve along with that. Okay. So hopefully that's helpful. Hopefully it gets you some insight as to how to approach these problems. Okay.